Professor Piya Pal is by far one of my favorite in the department. She holds the standards. If you take her class, who has taken classes with Professor Pal? Piya Pal, yes. How is she as a teacher? Excellent, thumbs up, absolutely. And high standards, hard exams, hard final exams, very high standards, like one of them said, like this, that high, yes, absolutely. No, there is no, she does not graduate wussies, that's for sure. And this is also shown in her work because, amazing, Presidential Career Award, Early Career Award, the Pierre-Simon Laplace, I love Laplace, award, and Fourier, okay, we have to say good things about Fourier. ONR Young Investigator Program, NSF Career, and so on and so forth. So it is with this, it's a pleasure to introduce Piya.
Thanks. Very, very generous introduction by Gabriel. There's a lot of pressure on me. I hope I can deliver. Okay, so this is the way it's supposed to work, right? Okay. Okay, good. So I just wanted to give you a brief outline of the kind of topics that I work on. I work on problems. I don't call them projects necessarily. I call them research questions, okay? So these are the main research questions that I work on. Today, I will be only talking about the one which is highlighted in red. If you go over the list, I'm not going to go over it right now, but if you go over the list, you will see that the primary theme of my research is information retrieval from measurements. And how you collect the measurement is the part where sensing comes into play. And how you retrieve the information from the measurement, a bunch of tools from statistical signal processing, estimation theory, etc., makes their way there. Okay? So it's a connection of both. Now, what is my unique point of view, or what basically I look for when I come up with new techniques, new ideas, is this quest for geometry and structure. Okay? So geometry and structure, this is basically what defines signal processing. Signal is not just some unstructured data. It has nice representation over certain domains, and using that representation, you can do a lot. Similarly, when you optimize, your optimization space has geometry. Your feasible sets, your constraints give rise to beautiful geometry. And the more you can exploit this geometry to your advantage, you can be resource efficient, you can lower your complexity, you can do many things. So how to use them in the best possible way is the main question that drives bulk of my research. So applications come and go, but this question stays, okay? So right now we are talking about sensing. I think it is not at all needed for me to justify that sensing is everywhere, 5G, going towards 6G. And I just listed some applications here, but the application list can really be endless, okay? And I think it was a very nice photo that I got from Qualcomm blog that kind of shows, okay, where sensing plays a role. So I will argue that you really need to be smart when you are trying to sense in the context of, let's say, next generation of communication systems and autonomous sensing, which two are the main drivers that I will talk about in this particular presentation. And the way you sense, there are really two main mechanisms that I will focus on. One is your spatial sensing, your antennas, or your sensors, okay? Your physical hardware antenna sensors. The other sensing, which is not so obvious, happens through your waveform that you send out. Okay, it carries information. If you can shape the waveform in a proper way, you can extract more information out of your target. It is very well known in radar. That's why radar waveform design is a very important topic. Now, when you combine the two, you can actually get amazing benefits. And this is something that I will try to motivate today, okay, using very recent work that came out of my group. Now, I will argue on top of that, in millimeter wave communication, you cannot even ignore the geometry in the channel. Okay? Why? Because you see, in MIMO, in lower frequency bands, the scattering environment is rich. So you could model the channel as a matrix, random Gaussian matrix, let's say. Okay? The matrix has structure, but you are not really harnessing that structure that much. It has structure in the terms of being low rank and so forth. Okay, that determines capacity and how many data streams you can put on the channel. But beyond that, we are not really exploring any algebraic structure of the channel. In millimeter wave, you have to, because the channel undergoes sparse scattering, so you have line of sight multipath propagation, and that propagation gives a certain harmonic structure to the channel, okay? Clustered multipath model. This is called the geometric channel model. And this makes a hotbed for array signal processing. And this is kind of one of my major areas. Statistical array signal processing has seen a resurgence in the context of millimeter wave communication because there's a real opportunity of applying decades and decades of wonderful research that has happened into this problem, okay? But I will claim that, okay, then where is the research component? It looks more like development and application. No, there is a lot of research component, and that is where the things becomes interesting. Because when you apply statistical array processing techniques on array signal processing techniques on millimeter wave channel kind of model, it comes with its own challenges, which makes it a very corner case application, okay? Which means you have a lot of constraints. Path loss, you have a lot of path loss, right? SNR, so SNR is constrained. Mobility, okay, you cannot ignore mobility. It's not a static environment. And mobility is, of course, relative, depending on which kind of situation you're in. Power and complexity. So all these things we have to take into consideration, and in this constraint space, we have to apply our statistical processing techniques. And this is not a simple plug and play. So the main question is how to be smart about resources without sacrificing performance, and that is really the holy grail, right? Everybody wants to be that, resource efficient and not sacrificing performance. Of course, you cannot get both of the both worlds, best of the both worlds, but you can certainly try to reach good trade-off points, all right? So what gives us the hope that we can be resource efficient and not sacrifice performance? It depends on performance with respect to which task. You see, the tasks that we perform, the sensing tasks that we perform often are not, it is not necessary to, to use all of the data, okay? Or use basically all the measurements that you collect, because your task may be simple in some way. I'm not saying the algorithm build is simple, but when viewed how many parameters you're estimating, it need not be too much. Let me give you an example of radar, okay? Radar collects data along fast time, slow time, and angle. Range, Doppler, and angle, basically, okay? But its goal is to localize sources. It collects radar data, 3D data cube. That is what is typically known. And you use space-time adaptive processing on top of that. But you see, your information content is small in the domain of representation. You're looking for x, y, z coordinates, or the range azimuth elevation angle of your target, and its velocity, okay? So few numbers. If your goal is to get this few numbers, what do you do with so much data? Or is there a way to be efficient beforehand, while at the stage of sensing, to actually perform this task reasonably well without sacrificing performance? I'm not saying I'm not going to sacrifice performance for any task whatsoever, but if I know my task, I can certainly be smart about my sensing. This is my goal, okay? And this is what I will talk about, enablers of smart sensing for communication and autonomous systems. So I will try to motivate this question by motivate the idea by throwing this question. So suppose our goal is something like a moonshot question, okay? But it is not moonshot actually. It is very much possible. So suppose your goal is to deploy only a few, let's say M, physical sensing elements. I will just call them sensing elements. It depends on the application; they can be different. And you want to harness the spatial sensing capabilities of order of M square virtual sensors. So in some sense, you can imagine, suppose I have deployed this red dots represent my physical sensors, and the black crosses represent what is not physically deployed. And somehow, by some magic, I want to operate with the combined spatial power of all the sensors that I have missed, okay? If I could do this, whether I can do this or not, we will look into it. If I could do this, what is the promise benefits, okay? Resolution, my God, I'm filling the whole aperture in some sense, okay? Ability to localize more targets and sensors. Yeah, physical sensors could be M, but maybe I can localize M squared targets, order of M squared. Low power, because I am not, well, low power is again debatable. After listening to Gabriel's talk, I will definitely not claim low power right away, but because you do computation, right? Computation takes power as well at the processor level, correct. So, so basically, however, this resolution benefit is kind of obvious. It doesn't require much justification there. Now, this answer depends. It's not an easy question, okay? Of course, it looks like a moonshot question. But if you could do this, the answer, whether or not you can do this, depends on the spatial sensing geometry. If you just don't want any specialized waveform design, just by manipulating the sensing geometry, can I achieve this? Yes, you can in certain operating modes. But now, if you have the ability to transmit and receive on the same platform, radar, autonomous sensing, right? You can actually be smart about how you design the waveforms. And waveform and array can match together and give you a lot of benefit, create the effect. So that is another way. Or like I said, both this array-informed waveform design, which is basically what is my current research right now. So the main idea why this is possible, let me try to motivate you. The idea is actually a combinatorial idea, okay? So suppose there is a set of physical sensors. I'm just drawing them in a line. Think of them as a line array. It doesn't have to be. It can be generalized to 2 dimensions and 3 dimensions as well. So you're allowed to place your sensors, location, within a certain aperture, however you want, okay? D1, D2, D3, D4, D5, whatever denotes the locations. Now, I claim that in certain applications, especially those pertaining to target localization, the physical positions of these antennas matter less. What matters is these two objects called their difference set and their sum set. So what is difference set? You take pairwise differences between the position locations. Sum set, just take the sum, okay? Now, if you do this, why do they matter? There is a math behind it. There's signal processing behind it. Why this quantity matters and not the physical sensors locations as per se. So if you believe that those two matter and not the physical sensor location, let's see what is the problem with spacing physical array uniformly. So uniform arrays form what is known as arithmetic progressions, okay? Which means the spacing between any two, so if let's say 1, 2, 3, 4, right? So 2 minus 1 is the same as 3 minus 2 is the same as 4 minus 3, it's arithmetic progression. If you consider sum and different sets of arithmetic progression, you cannot increase the cardinality because there are a lot of repetitions going on. 2 minus 1 is the same as 3 minus 2 is the same as 4 minus 3 is the same as 5 minus 4, etc. Clear? This is the main reason. This difference set has a lot of redundancy. So you cannot really create the effect of new sensing locations. However, if I give you the same number of physical sensors, but you distribute them in a different way, and one of the ways to do it is nested array, which was developed by me several years ago, then you can actually make the sum and difference set scale as order of m square. Okay? And this is the maximum, because you see, you consider pairwise differences, so the maximum number of unique differences could be m choose 2. So that scales as m square. You cannot be more than that, okay? Because it's a pairwise interaction. If you take 3 at a time, then it could be m cube. All right, so with this in mind, this basically, in the context of autonomous sensing, where you have a radar, and it transmits a waveform, okay, or form a beam, or use some of them to form a beam, some of them to transmit waveforms. This sum set can be realized, and this is done actually in the context of MIMO radar. I will talk about it, okay? And my radar does in a certain way, and my goal is to go beyond that, okay? Go beyond that and generalize and get better optimal points rather than just playing with the idea of orthogonal waveforms. So the idea is the sum set comes into play, and you can leverage the enhanced resolution or the localization of the virtual aperture with less. Less means with less actual physical sensors deployment, in that sense less. Now, typically what happens is, now let's see, what is the magic, right? There is no free lunch, so what do you give up, or what is needed? What is needed is temporal processing, okay? So you're trying to fill in missing sensors, or trying to create the effect, computationally trying to create the effect of what you lost. You cannot do it without spending a certain amount of temporal budget. So let me explain. So here what happens is, it depends on whether you're operating in the passive mode or active mode. Passive means you are not manipulating your waveform to do anything. Maybe you don't even have control over waveform, you're just passively listening in to the environment. Active mode means you are spending energy to design waveforms or to basically, form transmit beams to sense the environment. Both modes are important. You probably are more familiar with the active mode, but in defense applications, you'd actually prefer passive mode so that your presence is not felt. Okay? A radar also, when it senses the channel, sometimes it also listens in to get the idea of the ambient noise statistics. It operates in the passive mode. Okay? So there's the passive and the active mode. In the passive mode, the way to generalize this virtual array is by computing correlations between antenna pairs. So you take measurements and you compute cross correlations between different antenna pairs. And the more the number of unique correlation lags, the more is your ability to pretend that they came from some virtual sensing elements. Now, correlation computation comes at a price, because you need more and more data to get higher and higher accuracy of this correlation computation, and hence there is a temporal budget that is needed. Okay? So the idea is, if we want to use this idea for autonomous sensing or high mobility scenarios, can you do it fast? You have to do it fast, I claim. And have to do it, being able to do fast is good anyway, but it is almost a necessity in these kind of applications, with very few temporal snapshots. So basically this fast, how fast it can be, this has been on one of the major open questions in the research of the sparse arrays, there has been going on active research since last 10, 11 years. And this is a major argument. How can you make it fast? And like I said, it can be asked in two settings, with or without waveform manipulation. Now, like I said, the natural myth is to think that, oh, I have to create the effect of m² virtual sensing elements, so I need to pay a price proportional to the number of unknown parameters that I'm trying to estimate, correct? It's very natural. Statistics will tell you, of course. How can you get it? Absolutely right, it is true. If you want to compute cross-correlation between all possible antenna pairs, you certainly need your number of data to bring down the error, right? To bring down the error to be the proportional, at least, to the number of unknowns, correct? But we are forgetting one thing. Computing correlation is a means to an end. That is not our goal. Our goal is to target localization. Never forget that goal, okay? So if we have that goal in mind, my idea was to do the following. Let us create errors at the correlation stage with few snapshots. Sure, no problem, okay? And let's see if my geometry during the inference stage, where I actually try to estimate these parameters, can compensate for this error. If so, to what extent, okay? So imagine a pipeline. You have collected these measurements using virtual antenna in the sparse array, computing the correlation. After that, there is another algorithm that is running, right, that uses the correlation to actually infer the parameters. Yes, at the intermediate stage, you have large errors. But maybe those large errors are not that harmful. Maybe they are benign for the particular task that you have, and I will prove it to you. I will not leave it to you, leave this to speculation or experiments. I will prove it to you mathematically, of course, under my statistical assumptions, that it is possible to do so, okay? So this is my proof, because primarily I like doing theory, and this is the proof. So the proof is as follows. I will try to help you go through this, walk you through the thing, and don't worry about this, about the exact statement. You can worry about it. I'm happy to share the manuscript with you. But the main idea here is the following. Delta mean theta represents how your resolution is, the target resolution, okay, that you're hoping for. And P mean over sigma squared is an SNR condition. As long as your target resolution is larger, it scales as 1 over m squared, where m is the number of physical antennas that you have deployed, okay? And your SNR scales as 1 over m squared as well, okay, with different constants, of course. Then I can make my error go below any given epsilon with any probability that you want, 1 minus delta, provided my snapshots, my temporal snapshots, scale in the following way. So they have that the snapshots will depend on epsilon and delta, correct? That's, of course, expected in the following way. What you should notice here is the following, very important. How does it depend? How does this thing depend? How does L depend on m? As log of m squared. It's not m squared, it's logarithmic dependence. Why? Because my task is localization. And that in that task, I can afford to have my temporal snapshot scaling logarithmically in number of sensors. It's a very benign scaling. It's not at all proportional to m squared or anything, okay? Now, this is the myth versus reality. The small snapshot causes error at the correlation estimation stage, but it is compensated by the sensing geometry. So this analysis is actually not easy. This analysis, if there is a sloppy way to do this analysis, by which you will see that your L has to scale as m squared and not log of m squared. To do this analysis in a tight way, you really need a tight characterization of these restricted singular values of your sensing operator. And that requires tools from harmonic analysis, okay? Once you get a tight characterization of that, you can actually get a tight result. So this is the value of theory, to give you meaningful bounds. Without theory, you can do experiments all day, but you won't be sure. So I just want to kind of, cheer for theory a little bit here. All right. So ability to operate also, look, in low SNR regimes, my SNR scales, my SNR scales as 1 over m squared. So you give me more antennas? Yes, of course. It's obvious, right? I should have less SNR requirement. I can handle more noise. But look how it scales, not as 1 over m, but 1 over m squared. This is the size of the virtual array, right? So we indeed harness the degrees of freedom of the virtual sensing, and this is the trade-off. this trade-off is, characterization of this trade-off is very important. Okay. And these are some simulations. So the dotted lines, probability of resolution versus the angular separation, which is the resolution, which is basically the angular separation between the two closed clustered multipaths, two multipath components. So you see the, oh, what happened? Okay. The bold lines are this specific kind of sparse array called nested array, and the dotted lines are uniform array, okay? So you can see that the probability of resolution quickly goes up to 1, and look at the prediction around 1 over p squared. P is same as m, okay, in the number of senses. And there is a significant gap in terms of the angular separation that ULA and nested array needs to get to 1, probability of resolution being 1. And below what we have what is called phase transition diagrams, which shows you the interplay between SNR and snapshots, the signal to noise ratio that is needed, and the number of temporal data processing that you're doing. Look, at the separation, which is proportional to 1 over m squared, ULA is total failure. Basically, black dots mean it is failing. It's not able to resolve this. But nested array shows a beautiful phase transition, and I can actually tell you, analytically characterize what the shape of that curve will be from my analysis. Okay, that is the idea. Okay, yeah, thank you for the time. Now, can you do it with one snapshot? I think one of my PhD students presented this result in the open house yesterday. Yes, you can. But here the noise analysis is much more challenging, which we are currently working on it. Because if you give me some snapshots using some high-dimensional statistical estimation tools, I can get those bounds. But with one snapshot, you really have to be careful about how the noise distribution changes. Why is it possible? Why can you just with one snapshot get back? Because there is harmonic structure in the measurements. If I give you a wave, if you sample the wave sparsely, or a superposition of waves, if you sample the wave sparsely, you can predict the remaining elements of the wave in absence of noise, okay? Superposition of different waves. However, if you need uniform guarantees, this is work for all possible channel configurations, then you have to be careful about geometry. If you want, okay, this configuration works for this channel, another configuration works for another channel, be my guest. As many channels, as many sensing configurations. If you want to afford that, that's fine. But if you want one configuration to work for all possible unknown channels, then you have to be very careful about geometry, okay? And this is just an example. Using the sparse array, if you do matched filter is basically, phased array beamforming is one way to do matched filter, which means you want to look in that direction, you design a weight, and then sum it up. Because sparse arrays has a lot of, missing elements, it has grating lobes. So if you just do a beamforming with the physical array, you will have a lot of grating lobes and uncertainty. However, if you do this nonlinear interpolation, which is called Toeplitz completion, you actually get rid of that ambiguity and can localize a source. Now, whatever time is left, I will briefly talk about my joint work with my postdoc, Dr. Rayamaki, about this active array geometry informed waveform design. I really have very short time, so I will be quick. So you see, the results that I presented doesn't require active waveform. But if you have the ability to do active waveform, what you can do is you can either send orthogonal waveforms, receive them, bounce off the scatterer, have a matched filter, and out of the matched filter, realize a virtual array. This is what people in MIMO radar do. This is called orthogonal MIMO radar, okay? Other hand, you can do phased array, transmit beamforming. And this is a very beautiful thing, because you can now focus your power in certain directions. You cannot get so many degrees of freedom, but what you gain is SNR. Both are needed. You need special degrees of freedom, and you need SNR to get performance gain. But in different ways. They have different roles to play in characterizing your error, okay? So the point is, can I exploit the virtual array and boost SNR? Can I strike a soft spot? And my postdoc and I, Robin and I, basically tried to characterize what is a soft spot. So basically, it's a fundamental bound, okay? This is not algorithm specific. This is a fundamental bound that everything has to, that every algorithm has to obey. Spatial degrees of freedom versus waveform diversity. So the black dots represent the conventional points, full MIMO and SIMO, phased array. Now, if the point is, people used to believe that, okay, if you go, the only way to get full spatial diversity, full MIMO, is to transmit orthogonal waveforms from every antenna. What our analysis shows is it is not true. The optimal point is actually, this knee point. And how do I characterize this knee point? By looking at the redundancy pattern of my array, redundancy pattern of my sampling geometry. It is intricately connected to the array geometry. And the knee point is the optimal point to operate. Because at that point, you do not need to go full MIMO and use the remaining transmit antennas or the waveforms for forming phased array. So this is a beautiful sweet spot, not possible to get unless you do the math, okay? And now somebody may say, oh, this looks like multiplexing beamforming trade-off in traditional MIMO communication. Yeah, it looks like that. But you know what is new? In traditional MIMO, your channel is an unstructured Gaussian matrix. So yes, your diversity multiplexing beamforming trade-off will have a certain profile, but the role of the virtual array never emerges there because the structure is missing. If you have the structure, suddenly this trade-off curve expands and takes a different shape, which is guided by the array geometry. So antenna arrays play the role of in the traditional MIMO, it plays the role of this trade-off. It controls this trade-off to the extent of the rank of the channel. But here it is much more than the rank. It's a subspace structure, it's a harmonic structure, and there is a lot of things that you can exploit, and not just the rank of the channel. Okay? So this is what I say, that the structure, the geometry of the channel environment is what enabled this curve. And without that, you can, no. So basically, these are basically ways to show that, okay, how can you optimize for your waveforms and your transmit geometry. Anyway, I'll just stop here. The yellow line basically shows the optimized performance where we use part of it for special degrees of freedom and optimize the rest for the singular value. Thank you. I'll take questions. Sorry.
Thank you very much, Francesco Carbonante, aiutissimo. Very interesting talk. Can we use this type of approach to actually, for transmitting with arrays that are sparse arrays? Mm-hmm. So just as a transmission. So the same analysis should be able to be
absolutely. Done. So that's a very good question, and this is where this work comes into play. That sparse arrays, beam pattern is irregular. It's unpredictable. Why do you like uniform arrays? Because fast Fourier transform and sync beam patterns, right? You can actually do phased array and then just do modulation and change the beam pattern and look into different directions. Here, the beam pattern is more unpredictable. So the goal is to somehow synthetically, computationally stitch those, create the effect of, again, a uniform array by filling out missing holes. But it is not an easy task. It may not be even possible for arbitrary geometries. So if you are cognizant about the geometry, for certain geometries I can prove results which will tell you this is possible. For certain geometries, I may not be able to do that. So the design of the geometry is important here, correct. So transmit beamforming will be possible here.
And this is also for 3D spatial.
That's right, yeah, because these arrays can be, they can be generalized to 3D, correct. Mm-hmm.
Thank you.